this is going to be a quick go through on this Unit 6 Edexcel International A-Level paper. So it's from October 2021, and I'm just going to go through the answers. Okay, so this is for the Year 13 students. Okay, so the first question is to do with a heater. The heating effect is going to be investigated using the circuit shown. So the heater is the resistor here, which in the circuit is there. So the student investigated whether the temperature rise of water, delta theta, was proportional to the current I in the resistor. So the current is measured with the ammeter. For each value of current, the student refilled the beaker with water at the same initial temperature. So that's a controlled variable, making sure that we have I'm just trying to zoom in a little bit. That's the magnifier. Okay. Just so it becomes clearer when you're reading it. Okay, so that's a bit better. So this is a controlled variable that's starting with the same initial temperature each time. So they're going to do this with different currents, basically. So you're measuring the temperature change for different currents. So they want you to identify two other controlled variables. So the initial temperature is a control variable, and you could put volume or mass of water as one of them, or the time used, would be another control variable. So if, for example, you investigate the effect of the current, say for 2 minutes or whatever you want it to be. So that's another control variable. They've also accepted that they must keep the distance between the heater and the thermometer constant to make it a valid, fair test. It says ignore all other answers. So for example, you can't put anything else down. For example, keep the voltage the same or whatever. They're not accepting it. So these are the answers they'll accept. So you get one mark for that and 1 mark for that to get your 2 points. It then shows the student's data. So it says the student recorded the following data: current in amps, the change in temperature, and you can see that they've given 4 data points, and they want you to criticize the recording of this data by the student. Okay, so first of all, you could write there's an inconsistent number of significant figures used. So over here there's at 1 decimal place, then there's no decimal place here. So if they were doing 1, then they should have put 2.0 and 3.0. So you always use the same number of decimal places for the current. Common mistake made by students, especially in younger years. And then you'll notice there's only 4 sets of readings, so that's insufficient. So each of these will get you a mark. It's an insufficient range of data. So you could have gone, so I always say for A-level we want around 8, ideally 8 pieces of data to get a good graph. And then it says, instead of saying there's insufficient, you could also mention that there's no repeat readings shown. So for example, if they're doing these data points, then they should measure the temperature rise more than once, is what they're saying. And then a very simple one is the units are omitted for delta theta. So this should be presumably in degrees centigrade. Okay. So these were the 3 main points. That would get you 3 marks. Or you could say that the student should have shown the initial and the final temperatures in their table of data, so not recorded. So this would be an either-or situation, and same as this. So there's a variety of ways of getting 3 marks. Okay, so these are just basic skills that you need for practicals. So remember, this is the Unit 6 is the equivalent of Unit 3 in Year 12 if you're new to this exam. In Year 12 it's Unit 3, so it's the practical skills. These exams are 1 hour and 20 minutes long. Time doesn't seem to be a problem for students with these papers. Explain, it says, one improvement. the student could make to reduce the uncertainty in the measurement of delta theta for each value of current, okay, I being current. So first thing I put is stir the water, yeah, so that would reduce the uncertainty in the measurement of delta theta, or ensure the thermometer is close to the heater. There, as long as you got these two, but it says explain, so you can't just put the improvement, that would be state, okay. Explain means why. Why do you do that? So both of these would ensure the water is the same temperature as the resistor, because obviously the resistor is going to be hotter and you want the heat from the resistor to dissipate or spread out through the water. So this is the reason why you either stir or ensure the thermometer is close to the heater, okay. And then the second thing that you could do is it says to insulate or cover the beaker. So both of these are like a way of reducing. Why do you do that? Again, the explain is the why. Why do you do that? To reduce the amount of energy or heat transfer to the surroundings or the environment. So you either get the 2 marks for doing this with the explain why, or if you thought of doing this method, that would be your 2 marks. So each time you've got to state the improvement and explain what that improvement does in terms of the reading. Okay, looks like my computer is just frozen momentarily, so I'm just waiting to see if it's recording. Okay, looks like it's back. I don't know if you missed that. Just put this back up so you can see where I've given the 2 marks. So it's either these 2 ticks or you get these 2 ticks. You can't mix and match between them. So you either do the top half or you do the bottom half. Each time you must explain it. So it looked like the video just froze for a minute. Hopefully it will be okay. The next question is question 2, and it's about a pendulum. Okay, so pendulum length L, here it is, swings in a vertical plane. Yeah, vertical means up and down. The string hits a peg. This is the peg. Yeah, now, peg is just an obstacle. It doesn't say that. Presumably this is a solid piece there at a height h, vertically down below this. The point of suspension as shown here. So this suspended from the support here, and I'm assuming this peg is a solid obstacle to the pendulum moving from right as we're looking at to left. Okay, this makes the pendulum shorter for the second part of its motion. Yes, so it'll come this way, it's moving this way, it's going to hit the peg at this height, and then it's basically a shorter pendulum for the second half of the swing. First half of the swing, second half of the swing. Okay? So they want you to determine the period for the whole oscillation when h is 0.25 meters, this height there where the peg is, and L is 1.00 meters. Okay? So they're giving you 2 decimal places in your length measurements. Okay, so they want you to use the equation T equals 2 pi root L over G. And for the first half of the motion from here to here before it hits the peg, the period would be, so when it's long, the period when the whole length is used, okay? So I've called that the long period, the long bit of the pendulum, is 2 pi root L, which is 1.00, over 9.81 meters G, gives you a value of 2.01 seconds. So presumably you're going to get 1 mark for that. And then for the second half of the motion, which will be from here to here, it's like the pendulum has become shorter by 25 centimeters. So you do L minus H over G, so you're using the same. So I put it T short, so T long and T short. Okay, so that's what the S is used for. same in the mark scheme. So you put the same value, 2 pi, this time it's 1.00, the length is shortened by 0.25, divided by g, you'll get 1.74. And then for the whole period, then obviously this is only going this part for half the full oscillation. It's going to go there, 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 and back again. So for the half the oscillation, so each period will be in effect half of the value that it will take. So it'll go from there, it's be like half of the period there. So it'll be 2.01 divided by 2, and the same with the second half. It'll be 1.74 divided by 2, which gives you 1.88, and you can either use 2 or 3 significant figures, I would suggest, and that's how you get your 3 marks. So this is practicing using the pendulum equation, which is in Unit 5. Okay, so that's the beginning of question 2. The next part is continuing with the same pendulum question. The student suggests that an approximate relationship between the period t and h, which was the position the peg is placed, is given by t squared. Yeah, so it's not very easy to see. T squared equals pi. I just want to make sure I've got this right. I don't think it really matters, but it's pi. Looks like it's squared. It just looks like the photocopier I used was not that good in terms of the toner. Cartridge must have been running out. I think that says pi squared, and then 2L minus h in the brackets. So, and g underneath. So it says divide. It doesn't really matter because this is the equation, and you can still do the next part. Devise a plan to test the validity of this relationship. So is it valid? Using a graphical method. So this is devise a plan means write a method, and then you have to come up with a graphical method of what you're going to plot against what. Okay, so basically they want you to be able to use your knowledge that you want to get a y equals mx plus c format to this. Okay, so the first thing is you have to measure h each time you're doing this using a meter rule. So the variables is that presumably we're going to keep L constant. You're going to change h, so you can keep that as 1 meter, and you're going to say start with the 25 centimeters and then adjust the position of the peg. So you're going to change h. So obviously pi is constant, g is constant, L is constant, 2 is constant. So you have 2 variables, the t squared and the h are the variables. So place a timing marker. That's something to measure the pendulum against, like when you're going to start it. So, and you will need it at the center of the oscillation. Why do you need it at the center of the oscillation? Because that's when the pendulum changes from being long to short. So you want to have some kind of marker so you know when you've gone through the center and it goes from being the long pendulum to the short pendulum. Okay, so that's called a timing marker for those of you doing this in your second language. So you need to place timing marker, and in this case it has to be at the center of the oscillation. Then you then have to use a small initial angle of displacement. Why is that? Because actually the pendulum equation only works if the angle is less than 10 degrees. The mathematics doesn't work. The reason is air resistance becomes significant beyond that. So I always tell my students 5 to 10 degrees. So then you time 20 oscillations if you're following my instructions. At a whole number of oscillations, you want it to be longer. I always say 20 because human reaction time I always estimate to be about plus or minus 0.20 seconds. And by doing 20, and then divided by 20, you're actually dividing that reaction time of about plus or minus 0.20 seconds divided by 20. It makes your uncertainty for one period, which is what dividing by 20 does, it makes it plus or minus 0.01 in effect. Then it says repeat the previous step. I've put just to make sure, repeat this and calculate the mean period. So even though you've done 20 oscillations, you should really repeat it twice and then calculate the mean. Be careful you use mean, don't use the word average, because average could be a mode or a median. So these are different ways of getting 3 marks. Only going to give you 3 marks from this bracketed 5. And then it says that you often can start the timing, after the oscillations have started. So you basically get the thing swinging, and then when you're ready with your stopwatch, you can start it when it goes through the position that you want to start it from, which could be the center marker. Okay, so these 3 of these points will get you that mark. 1 for here, so 3 from this list, and that 2 more. Repeat the above method for at least 5 values of h. So you change the h, and the dependent variable, then t squared, will vary. And then you plot a graph of t squared against h, so because you want it to be a straight line graph, to see if it produces a straight line. So if it produces a straight line, you can then analyze it further, because the straight line means this and the y equals mx plus c format. Okay, and then you should be able to work out, if you do that, what the gradient would be and what the intercept would be by further analysis. So that's the 5th mark, and that's the 6th mark. Okay. Part C. Another student suggests determining t by setting up a light gate attached to a data logger. Okay. Well, they want you to discuss this time whether this modification would improve the investigation. So discuss means you have to do the pros and cons. Yeah. So it says using a light gate would eliminate reaction time uncertainties. Yeah, which is true. So that's 1. Then you can either do this bracket or this bracket. So here's one. Light gate. A light gate removes parallax error. Yes. Oh, it's my spelling mistake here. I've got light gates remove parallax errors because it is in a fixed position. The light gate is in a fixed position, and that's kind of a parallax error. Could be, if the human's doing it, is a random error. If you're out of alignment one way or the other, it could go. It could create an uncertainty each way. Yeah. Or you can say there would still be, I put still in brackets, there would be uncertainty in the time period, even though you're using a light gate, from the light gate, as, and this is the explanation, the light gate would time from the edge of the bob rather than from the center of its mass. So this is the kind of answer they're looking for. So you can either decide that you're going to get the 2nd and 3rd marks from the first brackets, or they'll accept this. So you only get 1. So you either do the top bit or you do the bottom bit. Okay, that's what the mark scheme is looking for. That's part C done, and that's question 2 done. Question 3 is looking at an oscilloscope, and is to do with sound. So you've got a microphone, a loudspeaker, and a bottle filled with air. The microphone's inside, and it feeds into the oscilloscope. So a student investigated standing waves using the apparatus shown. So standing waves, as you know, is where you have the waves going in from the loudspeaker and then bouncing off the end and creating a standing wave through the interference between the original source of the sound and the reflection off the side of the bottle or the bottom of the bottle. The signal generator was adjusted until a loud sound was heard. A loud sound means you're going to have reached a high amplitude on your oscilloscope at a particular frequency. So that's going to be one of the natural frequencies, or the natural frequency of the bottle of air. And then by doing that, it's called also the resonant frequency. So the natural frequency is the resonant frequency. So it causes some kind of excitation in that mass of gas, or that length of gas, if you like, or air. And it says, describe how the student should use the oscilloscope to identify the resonant frequency. So obviously, to measure the frequency using an oscilloscope, it's from the period. So that's just a note for me. Okay, so first of all, how do you find the resonant frequency first of all? So to find the resonant frequency, it's in brackets because you don't have to write this down. The key points are below, but to explain it, to show that you understand what you're doing, to find the resonant frequency, you would adjust the signal generator, to the point to find when the trace has the maximum amplitude. Yeah, so suddenly the trace, when you're at the right frequency, the resonant frequency, yeah, when you're at the resonant frequency, so I've underlined the resonant frequency, you're going to get a maximum amplitude. So you're looking for the maximum amplitude on the trace of the oscilloscope. Okay, it's very similar to the string experiment if you did one of the core practicals. Then, so you know we're looking for the period. So to get the frequency then, once we've got the maximum amplitude, you measure the number of divisions between two adjacent peaks. So for example, there and there, or you could do 1, 2, 3, and then divide the number of divisions. As long as you work out how many divisions there are between two peaks, yeah, you can then multiply them by the time-based setting. So one of these is a time-based setting, say it's this one, and it will tell you how much each division is worth. So for example, it could be 2 milliseconds. For example, each square is worth 2 milliseconds. So you count how many squares there are, those are called divisions, and then you multiply it by the time-based setting, which is per division. And that gives you the period, and then you have to calculate the frequency using the equation F equals 1 over T. Okay, that's 4 marks. So you measure the distance, multiply by time-based setting, and this is just to get the correct frequency. Okay, I'm not sure if I've shown you all that. Let me just go through that again. I was looking at the paper rather than looking at the screen. So you measure the number of divisions between the two adjacent peaks, or you could go all the way and divide by 2 to be more accurate. So that's why I put 2 in there, so 2 adjacent peaks. Adjacent means next is 2 successive peaks. And then multiply by the time-based setting, whatever is set on. Example, 2 milliseconds, 5 milliseconds, whatever it is. Then you multiply the number of divisions by whatever each value is on the time-based setting. That gives you the period. And then you have to calculate the frequency using F equals 1 over T for the final mark. Okay, so that's question 3A. Question B, the student reduced the volume of air, V, inside the bottle by adding known volumes of water. So he added water in, so basically the air height became less. He recorded the following values of frequency, resonant frequency, which is this, and against the volume. So this is the independent variable, this is the dependent variable, and for each value of V. Okay? They then tell you what to do. They want you to plot a graph of log F against log V. Now log means log to the base 10, yes? The alternative is natural log, yes, which is log to the base E. So they will allow you to do natural log because it will still work mathematically, yeah? So log to the base E is obviously, E is a special number in mathematics. So that's the one you use when you have capacitors charging, discharging, or radioactive decay. But this would be a normal log you could use, so log to the base 10, so log on your calculator rather than ln, so that's the key difference. It says use the additional columns, these two, to record your process data. Now, one key point, so they want 2 or 3 decimal, whenever you're using logs, you would use 2 or 3 decimal places, and all values should be 2 or 3 decimal places, okay? Make sure you know that for your core exam. Then when you do the log, you put everything there in brackets. That's the convention for logs and natural logs. So this would be log brackets V / centimeters cubed, and then it's log brackets F hertz. Okay, that should be a small f. Okay, so that's what they want you to do. You put the values in there, and I will show you the values in a moment. So if you get those two correct to 2 or 3 decimal places, you'll get 1 mark for each of those. Okay, there's your 2 marks that I've highlighted. It is the first 2 points of the 6. So they want you to plot a graph. So I'm going to show you, because I haven't plotted it myself, I'm going to show you their values. Okay, here is the log graph and the log table. So this is their table. See the way they put the brackets? They put the log to the base 10, the values in there, 2 decimal places, 2 decimal places. So it's the number of decimal places that is key here rather than significant figures. Once you got that, you then have to see, well, it ranges from about 2.1 to 2.76. You do not need to go down to 0, okay, because you're just looking at the change. So this examiner has put 2.3 at the bottom and 2.7 at the top, yeah? So that's log f, so I'm looking at the wrong column. So this log f he's put on the y-axis. Now if you remember, it says plot log f against log v. That means the first one goes on the y-axis. That's my mistake. So log f goes on the y-axis. That goes from 5.4. Sorry, I'm looking at the wrong side. That's the natural log. The log f, which will be on the y-axis, goes from 2.34 to 2.69. So he's gone from 2.30 to 2.70. Make sure you have a sensible scale. They don't like you using any number other than the scale to be 2, 5 or 10. So in this case it's a 5 multiple of a 5. So 2.50, 2.5, 2.30, 2.35, 2.40. So that's what they mean by a sensible scale. Okay? I always tell my students 2, 5 or 10 is what you should be using for these squares. And then log v, they've gone from 2.1 all the way to 2.8. Look at the original data in the table. It goes from 2.10 to 2.76 for log v on the x-axis. Okay? So remember, this is the independent variable, log v. So that's also why it goes on the horizontal axis. Once you do that, you plot them, you should get a straight line with a negative gradient. Okay? Show your values, because you're going to have to work out the gradient. Show your values and use a large triangle. And they've done it from 2.4 to there. Yeah, so they've shown where they get their readings from. There's their delta x. There's their delta y. Yeah, so it's shown quite clearly on the camera. And then they do their gradient calculations on the graph. It's always a good idea to do it there. And once you have this data, yeah, how do you get the marks? Going back to so for the marks on the graph, if both axes are labeled correctly with brackets as shown in the table, yes, you get 1 mark. Correct sensible scales, as I just discussed, for both axes, yeah, good round numbers, 1, 2, 5 or 10 changes in per square. Plots are accurate. What they'll do is they'll look at any points which are far away from the line of best fit, and they'll look at those ones, and if you're more than 1 millimeter out from their judgment, you will lose that mark. And then the line of best fit, you need an even spread each side of the line. Okay, so once again, looking at their graph, you will see they have a good line of best fit. Yeah, this one is a little bit below, this one's a little bit below, this one's a little bit above, this one's a little bit above, this one's slightly below. So it's a pretty good fit. Okay, now if you've done natural logs, they've also given an alternative table where the students may have got confused and put their values in natural logs. So you'll see even the tabulation of natural logs still has the frequency and the units inside the brackets for both the frequency and the volume. So this they've just done ln, ln, so it will still give you the same shape graph. Yeah. And here you see they've done again a very big triangle, and they've shown they're working on the graph, and this time they have sensible scales going up in 0.1s and going across in 0.2s. Okay, again they've shown delta x and they've shown delta y on their graph, and they've done the calculation. This one was 0.51, and they're showing you that it's negative, and the other side gives you a minus 0.53 using the logs. So how do you get the marks for this? So we know how we're going to get the marks for the graph, so I've just written it out there. There's your 6 marks if you get all of that. And then they want you to then do your analysis. So it is suggested that a relationship between f and v is given by f equals k v to the power of minus a half. So if you do that, you take logs, it will be log f equals log k minus half times log v. Okay, so if you don't know how to take logs, you need to go and practice. Well, this is the intercept c, because that's a constant. We put log f on the y-axis, remember? And we put on the x-axis log v. That means the gradient should be about minus a half. And you saw the two graphs, one was minus 0.51 and one was minus 0.53, the way they'd calculated it. So you have to discuss where k is a constant, yeah, so that's the intercept. You have to discuss whether the graph supports this suggestion. So you would say, if you take logs, as shown above, graph is in the form of y equals mx plus c. Yes, you need to state it categorically. You need to make sure you don't leave anything unsaid or unwritten. With a gradient m of minus a half. So my m has become a little unclear. So that's meant to say m is minus a half as shown above. Okay? And then the gradient calculated from the plotted graph, yeah, you get 1 mark for showing that the gradient is calculated from the plotted graph, is producing m in the range, as long as you're between 0.51, 0.54 and shown the minus 2 or 3 significant figures, you'll get so 2 marks for this part, 1 mark here, 1 mark there, and then you make a valid conclusion, which is by comparing the calculated gradient with the expected minus a half, and you say they're very close, yeah? And that will give you your 5 marks. Okay, that is question 3, yeah, shown on the graphs, and the next part is question 4, which is the final question. This time you got an L-shaped steel rod, which is this L-shaped steel rod there. It's clamped as shown at its shorter end. Looks a bit like an Allen key. For those of you who know what an Allen key is, like you get them in IKEA when you buy furniture. And it was held in using this clamp as shown here. Okay, so they got 2 clamps down, one holding the ruler and one holding the steel rod which we're investigating. It says the end of the steel rod was at a height P, yeah, see the dotted line to show that you're measuring against the ruler, above the bench, okay? So you put the ruler on the bench, and then a student attached a mass M to the end of the steel rod, so presumably they mean here, causing it to bend towards the bench. Well, so it's going to bend that much. So imagine it's going to bend up to that point Q. Okay, so the mass is pulling it down. Must be a big hefty mass or a very weak thing, so it's going to go down and it's eventually going to be, say, moved down that much. So it's causing it to bend. Okay, that's what's happening. So it goes from P above the bench to Q above the bench. So causing it to bend towards the bench, the end of the steel rod was then at a height Q above the bench, as I mentioned. So you've got the 2 heights. They want you to say, describe 2 techniques the student should use when measuring P and Q. Okay, well, this is what they're looking for in the mark scheme. Ensure the meter rule, this one, is close to the end of the rod. So make sure you move the stand close so it's easier to see where this dotted line would be. Yeah, so this is 1 mark. Or you could say use a set square to ensure, so you put your set squares, for example, if you've got your set square there, you could make sure that you're reading it straight against the ruler. But again, you do want them to be quite close, so that's just common sense. Use a set square to read off the values at P and Q using a set square. So you move the set square down for P and Q to make sure you don't have any parallax errors when you're reading it. So either any of these statements, the or statements, will get you the first mark. And the second mark is the second arrow. Ensure the meter ruler, or the meter rule, is vertical. Yes, you want to make sure it's not at an angle. Using a set square, so you could also use a set square by placing it there to show that it's at right angles to the bench. Okay, that's the second mark. Okay, it's all common sense. And then the difference between P and Q was recorded as being 26 millimeters plus or minus 1 millimeter. So that's the uncertainty. That says plus or minus. Again, the font isn't that clear with the photocopier I used. So to explain why the uncertainty in this value was given to be 1 millimeter. What they want to check that you know for this exam is A, what is the resolution of the meter rule? Well, the resolution of the meter rule is 1 millimeter. But the uncertainty, according to this exam, is that the uncertainty of each measurement is half the resolution. So they're saying, why if you put 1 millimeter, half the resolution would be plus or minus 0.5 millimeters. Okay, so then you've got to say, but as you have to make two measurements, one for P and Q, to determine the difference is P minus Q, each one will bring in half a millimeter of real uncertainty. So what you do is you add the half a millimeter for the P, half a millimeter for the Q. So the difference, let's say Y, I think it comes out as they're calling it Y later on. So your real uncertainty in Y would be plus or minus 0.5 millimeters, plus or minus 0.5 millimeters. So that means it could be plus or minus 1 millimeter in total. So that's the justification of why it's given as 1 millimeter. Okay? When you're adding two values, you add the real uncertainty if they're in the same unit. So that's question 4, the start of question 4, and then question 4 continues. The steel rod had a circular cross-section, yes? So that means cross-sectional area, with a diameter D of approximately 2 millimeters, okay? So D is approximately 2 millimeters. So this is approximately equal to 2 millimeters for D. So it says explain, so I'm underlining explain, the most appropriate instrument the student should use to measure D. So they want you to know the most appropriate instrument. Well, that's a micrometer. Okay, that's normally what you would measure a small cross-sectional area, which is about 2 millimeters. But you could use digital calipers now, because each one has a resolution of 0.01 millimeters. Don't get confused with digital calipers rather than vernier calipers. Vernier calipers are using the old method of doing them. Now you've got digital ones, they're 10 times more accurate. So only digital ones can equal the resolution of a micrometer. So you're saying what is the most important ones, that's stating it, but they want to explain. So be careful when they say explain. And then you say, as this would produce an uncertainty of 0.01 out of 2 millimeters, which will give you a certain percentage, which is very small. Yes? So they want you to talk about the uncertainty being very small. So in the mark scheme, they've actually calculated what it is. Yeah? So you could actually calculate it. So remember what I said, drive the point home to make sure that they can't have an excuse not to give it to you. So the next part, again, it's got an explain. Okay, so here was an explain. So they don't want you to just say it, they want you to go all the way and say why you're doing that. Okay, so explain means going a little layer deeper in understanding. Explain one technique the student could use to measure D. Okay, so the normal method would be repeat at different orientations or positions along the L-shaped steel rod and calculate the mean. Again, remember, make sure you put mean and not average. So you repeat at different positions or different orientations. So it might not be perfectly circular, which would be an orientation issue. So you do it at different angles, and positions, it might not be of uniform cross-section area perfectly. So either of those will give you the mark. Why do you do it though? To reduce the effect of random errors. Okay. So it could be that you one bit is slightly out, so one bit might be slightly thinner than the other bit, and so on. So that would be a random error because it could be one way or the other. That's what a random error means. Or, so this is your 2 marks. If you do that, you get 2 marks. Alternative method is check that your micrometer has no zero error, or vernier caliper. Vernier calipers, not vernier caliper, digital calipers. They actually are digital, so you can actually you can reset it to make sure the zero error disappears, to eliminate, so check and correct. Yes, for zero error, 1 mark. Why? Explain. This eliminates systematic errors. If you've got a zero error, it will always give you the same error if you don't correct it. Okay. So for example, the micrometer is reading 0.01 before you start. You just need to take 0.01 off your reading to eliminate the systematic error. Then it's given you some data. The student has done it in 5 different positions, 1, 2, 3, 4, 5. If you add the sum of those up, it comes to 11.74, which we're going to work out because it wants you to calculate the mean value from the data they're given. So you've added them up, 11.74 millimeters. Divide them by the 5 pieces. There were no big anomalies in there. Gives you 2.348 mathematically. You round it up to 2.35 because that's the accuracy of your tool or the precision of your instrument. Okay, so once you get that, you'll get 1 mark for doing that. And the range of data, because they want you to give the value and its uncertainty. So the uncertainty is half of the range of data. Well, the range of data is the maximum 2.37 minus the minimum, which is 2.33, which gives you a range of 0.04 millimeters, and the uncertainty is half of the range divided by 2, so that's 0.02, so you put 2.35 plus or minus 0.02. That gives you a percentage uncertainty, we're going to do that for later, of about 0.85%. So this is 0.85% uncertainty. Yeah? So why am I telling you that? Because the final part of the question, it will go into that. Part C, they're talking about shear modulus. Okay? It's another measurement to do with the material technology. So G is the shear modulus, is a measure of the material's resistance to bending and is given by the formula 32 mglx squared over, so this is a squared, and there's pi yd to the power of 4, believe it or not. Okay, so they're giving you that formula where m is the mass attached to the end of the rod and y is the vertical deflection, so that would be p minus q, is what I told you before. And L and X are shown on the diagram as being the 2 dimensions of the steel rod that we've been dealing with. Okay, so they want you to determine a value for G in newtons per square meter. Okay, that's newtons, meters to the minus 2. They've given you the mass of 100 grams and it has negligible uncertainty. Yes, so this would be in kilograms. The length is given in centimeters. You need to change it to meters. The x is given in centimeters, so you need to change it to meters. And this is in millimeters, so you need to put it into meters. So they're checking that you don't fall for that trap of not changing it. Put all the numbers in the equation. Yeah, put them in correctly. So remember, one is squared and one is the power of 4. I haven't bothered writing pi out. You put it in your calculator. The calculator, it comes out, the top comes 0.196, the bottom comes to 2.49 times 10 to the minus 12, and the answer is 7.87 times 10 to the 10, so you can simplify it to 2 significant figures if you so wish. I think 3 significant figures would be fine as well. Now, so why are they giving you all the uncertainties here? Because they're going to go into uncertainties later. So what I've put at the bottom of this page here, because there's a little bit of a gap, what about the uncertainty in this value? How certain is this value that we've calculated? Now you have to remember that to work out the total percentage uncertainty of G, you've got to be able to work out all of the uncertainties one by one. The percentage uncertainty of L, because that's in the formula. Okay, so going back to the formula at the top of the page, remember it's got 32, no uncertainty, M, no uncertainty, G, no uncertainty, L, X to the power 2, pi, no uncertainty, Y, we did before, we had it on the page before, and D to the power of 4. So when there's a power, it's actually 4 times the percentage uncertainty for D. Okay, so it's the percentage uncertainty of L, 2 times the percentage uncertainty of X, because that's in the term, is squared in the calculation for G, and then plus the percentage uncertainty of Y, and then 4 times the percentage uncertainty of D. Now where did we get the percentage uncertainty of D? It was on the page before, where we worked out D as being 2.35 plus or minus 0.02, which I said was 0.85%. Okay, so that's where it comes from. That's why I did that before. So once you do that, if you put all these values in here, the values are given to you with their uncertainty. So I've done it here. This one is 0% because the mass it tells you is negligible. 0.17% is that. 0.97% is that. And 3.85% is the y value, is the uncertainty there. So once you got that, the only uncertainty you don't have is the d, which was here, which was 0.85%. Okay? So I'd already calculated all those because I knew it was coming up. And if you add up all those percentage uncertainty using the formula that I told you about, it comes to 9.36%, which is approximately 9.4%. Okay? You don't ever want to have more than two significant figures for when you're actually working out percentage uncertainty. So this is a treatment of uncertainties, which is very good for you to make sure you know how to do. The final question then is part D. It gives you two values of D for different types of steel, structural steel and carbon. One is got a G value of 79.3 times 10 to the 9 newtons per square meter, and the other one is 77.0. Okay? They want you to deduce whether the data provided in part C would allow the student to determine the type of steel that the rod was made from. The answer is basically no, because if you know the total uncertainty was plus or minus 9.4%, which is what you need, so they'll probably give you a mark for working out the 9.4% at least, then I didn't use the 7.9, I'd use the 7.87, the three significant figures value. If you do 7.87 plus 9.4%, and that will be the maximum value, comes to 86.1, yes, in the scale that they're giving here, times 10 to the 9. So I've changed from 10 to the 10 to 10 to the 9 to match the data given in the table. So that's the maximum value. It will be plus 9.4%. Yeah, so that'll be 7.8 plus 9.4% of that, and then put in the correct indices. And then you take away 9.4%, so it'll be minus 9.4%, 7.87 minus 9.4%, and to nano would be to 10 to the 9, I mean, would be, which is giga, would be 71.3. So you'll notice 71.3 and 86, both these values are within that range. So as the range of the calculated values, from part C, 9.4%, covers both values provided in the table above, the student would not be able to determine the type of steel. So that's one for the conclusion, one for working out the maximum, one for working out the minimum, or that kind of mark. That's how I would do it if I was the examiner. There's your 4 points. And that is the end of this paper. Total is 50 marks. So I hope you found that useful. So please like and share the video with any people taking the same exam. And if you want to know when the next video is ready, make sure you're subscribed, because I'm going to do more videos over the next few weeks because it's a spring break and a lot of students are getting ready for their exams. So thank you very much for watching, and hopefully see you in the next video. Bye for now.